I think we are okay now. There is a problem because this is Mac and the help or something that is not compatible with Windows. Well, I'm glad to be here. Nice to meet you. Thank you very much for your participation. Today we will examine the problem to how we can forecast an unknown event. And this event is included in a time series, in a univariate time series. This time series must be any physical phenomenon. Maybe it's the time evolution of a cell, the time evolution of an earthquake, the time evolution of EEG from rain recordings, and anything that changes with time. We'll try to face the problem with two methods. The first is to examine if this time series is chaotic or stochastic, and if it's not random, we have the possibility to make a short-term prediction. If the time series is a random or stochastic one, we can do nothing, because this is a random one. We'll try to examine, to investigate if there is a chaotic nature, and if exists the chaotic nature, we can predict. The second method is to use neural networks, and with artificial intelligence, we will try to do the same thing. And the good one is we can combine the two methods, taken information from chaotic dynamics, and this information we will use to establish and make an architecture with neural networks. Well, I will inform you that the codes that we will use to forecast the series, I will upload in a Google Drive. There are existing Google Drive, and there are codes in Python and R, programming language. Okay, are ready to use to make the predictions. Well, the problem is this: I know the time evolution until this time moment, this day, and I want to predict and see what will happen the next day, the next time step, the next month, the next year. There are many possibilities. Look, we'll go up, we'll go down, we'll remain steady. We don't know. This we will face. The challenge of forecasting, there are many forecasts that failed in history. As an example, the chairman of IBM said, I think there is a world market for maybe only five computers. It's ridiculous. Computers in the future may weigh no more than 1.5 tons. And the magazine Popular Mechanics. And the last one is that there is no reason anyone would want a computer in their home. This was failed forecasting issues. Okay. To forecast a time series is more art than science, and you will understand it in the formula. Well, what is easiest to forecast? The temperature, the maximum temperature of tomorrow, daily electricity demand, stock price, And what we mean with the term easy or the term easiest? And what makes it to be difficult or easy? The factors, the forecastability factors are if we have a good information, a good understanding about the value, the price that we want to forecast. If we have a lot of data, if we know more past, we will be able to predict the future. If the future is similar to the past, and of course the forecast cannot affect the things we are trying to forecast, but this is a question about this. We will see and face it later. Well, the key point is to understand the complexity of the phenomenon that we want to forecast. If the phenomenon is complex, and this means is a hard one, that means that there is exists the phenomenon of butterfly. Small changes can lead to dramatically different outcomes. Long forecast is impossible to achieve, but short forecast is possible if we are good to understand the nature of the time series. Well, we must clarify the term complex, the term complicate, the term random. Well, if our system includes few variables that describe its evolution, and the correlation between these variables is linear, then we can say that is a normal system. If we have many variables and the correlation between them is the same, is linear too, we have complicated behavior. If we have many variables and the interaction between them, the correlation between them is nonlinear, then we have the stochastic or random process. This is impossible to predict. This is a random walk. But if we have few variables marked, and the correlation between them is nonlinear, then we have a system that we call it complex or deterministic outcome. So, we will investigate this part. Well, the difference. What is a complicated and what is a complex system? Complicated system is a microprocessor. Its function is difficult to design and understand. Okay. But the behavior is easy to understand. It makes arithmetic, numerical procedures. If the system is complex, as the combination of two pendulums, the function is easy to design and understand. Put two pendulums together, but the behavior is difficult to understand. We cannot predict the evolution of angular versus time. It is without system. A car engine is complicated. Many parts with clear functions and predictable behavior. We know exactly what the car machine do, but an ant colony is a complex system. What is the difference between linear and non-linear? In this figure, there is a linear evolution of a system. A difference between the two trajectories keeps on increasing always. So we can say in the future that the distance will be larger than before. But if the system is non-linear, there is a part of it that the difference increases, but here decrease. We cannot know what will happen in the future. Well, what is the chaotic system? The chaos means that the system has a sensitivity to initial conditions. Nearly identical initial values lead to very different final values. There is a deterministic nature because we know the differential equation that describes the phenomenon. We know. And its behavior, as we said before, it is complex. The first one that studied the chaos was Henry Poincaré, that he tried to research. Its research was about the three-body problem. But in this time, there are not computers, and he cannot, its differential equation cannot solve arithmetically. Edward Lawrence was the pioneer that he investigated, and it is famous about the butterfly effect. He studied climate change and understand that a small difference in initial condition of its differential equation lead to very different results. And here we have the butterfly effect that he said that when the butterfly will make a hurricane in London. Can you see no, this is we see in this picture clear. Well, we have two sets of data that they have the same mean. Average value is identical. The variance is the same, and the power spectrum is the same. This data 1, this data 2. The data 1 is the product of a random process. Okay? The data 2 is exactly the same, but you cannot distinguish looking at it, but has a complex behavior. It follows specific mathematical rules. This is the rule. The new value of x is the previous value in this formula. It's a clear deterministic process, but it gives this time series that is identical to the previous, which is a random process. Well, in order now to find and examine and take information about the chaotic system, we use the term of phase space. What is the phase space? Phase space is a Cartesian coordinates that in every axis we have the real value, the measurement, the experimental value, x versus t, and we do this. We recreate, we make another value. How? instead of time t, we add this term. And again, we recreate another variable using this term. This is a characteristic time. We say it delay time. So we move in time the original time series with this and make two virtual time series. Why do this? If we have a system and we do not know how many variables are needed to describe it, how many differential equations we need to describe it, the number of differential equations, first order, 3, 4, 5, 6, we don't know nothing about it. We have only this information. There is a theorem of Takens who said if we recreate, if we reconstruct new variables, moving the original time series in time two times the delay time, 3 times, etc. This new virtual variable has the same topological properties with the other unknown real variable. The question is how many variables we need. Do you know before the number? No, you don't know, but you can find and say that this unknown system can be described with 3 or 4 or 5. Only the number we know, nothing else. And we can do this using the Taken theorem, constructions from the single measured values. Every point in phase space has this coordinate. Well, in summary, Taken's theorem states that you can obtain a structure that is topologically equivalent to our phase space image. This is called attractor because there are areas in phase space that the trajectories, there is points that, an area that all the trajectories are attracted. So we call this image attractor. If this image is a circle, this is a periodic system. If the attractor is 2 circles, means that there is a periodic system with period 2. If there is a strange one like this, we call it strange attractor. If the system is random, all the points cover all the phase space. There is not a pattern. If we see a pattern like this, then we know exactly that this is a strange attractor and the system is chaotic and there is the possibility to predict. So, well, the number of variables, 3 in this case, this is the Lorentz strange attractor, and it seems like butterfly, as you see. Well, if we have the number of 3 variables, means that the attractor lives in a 3-dimension space. This number called embedding dimension. What is the dimension? Is the number of variables that we need to describe, to understand the dynamic of the system. Well, the problem is to find the delay time that we can move in a time window, so with the help of the delay time, to reconstruct the phase space. Here we have 4 cases using 4 different delay times. This is a projection in a plane. It's 2-dimensional and it's called phase portrait. In this case, the delay time is very small. Here, the delay time is very big. And here, the correct is this. This is the attractor of Lorentz. If we have a small delay time, we have this, and we have not a clear information. Same here. Okay. How we will choose the correct delay time? Imagine that we try to measure the temperature every second. Do we have any information measuring the temperature every second? No. The information that we have is the previous. Let's not change every second if we measure the temperature. If we measure the temperature every 12 hours, what happens? We lose the up and down values, the high and low temperature every 12 hours. 12 hours mean this, big delay time. 1 second means this. The correct delay time is to measure the temperature every 3 hours. This is corresponds to this phase point, which is the correct. So the problem is to find the optimum delay time. For this purpose, we use a function called mutual information. The mutual information says, the function of mutual information, we see next, says how many bits of information can obtain about the value in time t this time if the value is known. The previous value is known. How many bits of information? Every second, if you measure the temperature, there is not bit of information. Every 12 hours, if we measure the temperature, we lost the bit of information. The theory well says that the first minimum of this function gives the correct time delay. The first minimum. Also, we can use to find also the delay, the optimum delay time, another function, the autocorrelation function. The autocorrelation function gives us the linear relation between values. The mutual information gives us the nonlinear relations, interactions between values. The autocorrelation function gives the extent to which observation in a time series depend on each other. Each observation depends on previous ones. We can use the ACV to find the optimum delay time. Usually, the first zero crossing gives the optimum delay time, or the value of ACV that is the one of, this is the base of a Neper logarithm, the 1 divided by E of its maximum value. All these are starting points. In practice, we use values that are near the starting point values. what the autocorrelation function really means. Here we have a family of monsters. Okay? The current monster, its parent, grandparent, grand-grandparent, and going back. First autocorrelation example shows correlation over different time lags. Well, this is not similar with this. The time delay is 1. The time delay is 2. The time delay is 4. So, this is very similar to his great-great-grandparent. We are very similar. So, which is the delay time that gives the best relation between the monster? The 4. 4. 1, 2, 3, 4. Okay. At the lag 3, look this also. The correlation function, it is possible to take negative values. Negative value, see, it means that there is no relation between the 2 points. This is a negative value, okay, this is a positive value. Well, here is the mutual information function. Its formula is this. As we said before, the mutual information gives us the information that it's distributed between x and y and c. And if is 0, the 2 variables are independent. Okay. Well, what in practice we do? Apply the mutual information to time delayed versions of the same vector. We plot the function versus the delay time, and we find the first minimum. And it gives us the optimum delay time. Well, we can see and compare the 2 different states. In the left panel is the random, the stochastic time series. If we make its phase space, how? If we plot a value versus, I will use 3 because the delay time is 3. Here is the big question. How many near neighbors? Let's try with 3. Number of future predictions. I'll choose 10. Here is, as you can see, the training test points is the green and the blue, and the red point here is the prediction. The prediction is 10 points in future. How good is this prediction? let's face it. I open the Excel. This is the time series that I used. This is the time series. I used until to a thousand This is my last known point. I want to see that next 10 points are exactly these points. For this purpose, I copy these values, copy, go to Excel, paste in this place, and try to understand how close are these points. And the best way is to take a plot and compare. Insert this. This is the prediction of unknown points. It is not good, very good, if I try to change the number of neighbors or the delete time, I will have a better prediction. But mark me, we must focus on the trend, not on exactly points, the trend. What is the trend? The trend is a decrease. Here increase. I don't care about the exact point. I care about the trend. Okay? And the trend is captured here. There are another algorithm. I will keep it for future. I'll use another KNN algorithm. KNN. This. It's a variation of. Let's try the same 5. No. Why no? Because I used the Windows path, but here we are in Mac. Chaos T mean test of T, txt. Again, Windows size, I'll change it, I'll use 4. I use 5. and again 10. Okay, we don't need it. Let's see a different prediction using different K and N and different delay time. Compare all. Let's do the plot again. Let's see. The actual is the blue. The second column is the red. And the new prediction is the green. As you can see, it's better than the prediction using K3, KNN3 and a bending and delay time 3. Okay? This is the procedure that someone must try using the phase space reconstruction and make the predictions. As you see before, it is a little trial and error. Okay? The question is always, what is the delay time and what is the number of K and N? But I have information about the delay time using the mutual. It's more difficult to use versus Python. You write a script in a text editor, copy the script to R, I'll do the procedure, and automatically run and take the results. Well, there are two scripts in R. The first script is to test if our parameters are correct to predict using the phase space reconstruction. So the predictions is in sample. And if we are all right with this, we will use the next software that predicts out of sample. So let's try to use the in-sample software. For this purpose, this is the text, the code in text form. It must be loaded by two libraries. Look, the point is n steps means predicting steps, 10 steps in the future. Going here, here is the embedding dimension, as you said before, I used 5. The time lag is the delay time, used 3. The other we don't change. Prediction step is 1 is iterated by 1. So we don't need to change this. So we must change the embedding dimension, the time lag, and the number of steps that we want to predict. We copy the text, copy, from any text editor. I take it, copy, I'll go to R, paste it, and enter. It asks me to load a file. It is not command line as before. To load the file, I will load the same as before, this. And here is the in-sample prediction. It's not very good, but it's okay if we play with the real neighborhood lag and we have better prediction. And if we are satisfied with embedding dimension and delay time, that we keep these parameters. The next step is doing out-of-sample prediction. This is in-sample prediction because we know the real data. So, I close it, Here is the mean absolute error. You have this information too. And I'll take the other code in R, all of this in sum, out of sum. These are not needed because already are provided, but in your file on Google Drive, the installation exists. Again, the same procedure. I will copy this. Again in R, just paste. Enter. Again the same file. And here is the out of sum prediction. So you can use the R and the Python codes. Try this to be familiar. We return on presentation on PowerPoint because the time is past. I'll go to the next step. And the next step is the neural networks. Is the neural network. What are the artificial neural networks? How we recognize a face, a person? How we understand that this is a human, this is a man, this is a dog, or this is a flower? The brain takes information and make a classification. If the information has a pattern with 4 legs, this is a dog, animal. If the pattern has 2 legs, this is a human. If the pattern has, I suppose, long hair, is a woman, etc. So, I see a person. I know him. I know his height, his weight, the color of his or her eyes, the face characteristic. And I know this is, as example, Mehmet. I know he is Mehmet. Okay? But I have myopia. So, if I remove my glass, I cannot take a clear information. I'm not sure who is he. But this information that is not complete, the brain make a prediction and says, oh, this is Mehmet, because has a supervising learning before that when see this characteristic, his eyes color, his height, how he walks, understand the brain that this is making a classification of Mehmet. Without the correct information, if I put my glass out, it is capable the brain to predict this image and says this is Mehmet. if the image is the person is very far from me, and I cannot see him very clear, I cannot predict. But if it is in a proper distance, with information that is not complete, I can predict. This procedure of prediction, of classification of human brain, we try to mimic using an artificial brain and using not the biological neurons that our brain has, but we use an artificial neuron that makes the same job. The idea of artificial neural network is to learning from data instead of explicit programming. The neural network learns the relation from examples by supervision. There are, of course, neural networks that they may not need a supervisor. We can use neural network to rescue image processing, interconnected structure, and the base idea is to learn from experience. This is the biological neuron. There is an axon that through this the information is transferred, and the information is millivolt, is voltage. Here is the cell body, that here is the processing, and the processing out to firing or not the neuron, transfer or not the information to another neuron, and the other neuron to another, and make a network that the information is transferred. Here is the artificial neural network. In biological neural network, this is the inputs, and this is the output. The inputs are the sensors. I see with my eyes a color. This is the information. This information is transferred in millivolt through the other neurons going to my brain, and my brain is supervised by its contraction to understand that this is the color red or the color green. The artificial neural network has the same, do the same job. There are the inputs. Every input is more significant than the other, so we take a weight. Here we have a summing functions, x1 epw1 sin x2 epw2 sin x3 epw3. There is a summing function. There is a computation, and here is the output through a transfer function. What means the weight? When I see a dog, it is important to see if it has a tail. Okay? Not ears. The human has ear too, but the man has no tail. So the information about tail has a larger weight, a bigger weight. The information about this is smaller. Now, if the information can be transferred, if the neuron firing or not, it depends on the transfer function. The input, as said before, is the weighting sum, and the activation function is a function that takes the input and gives an output. The neuron collects values from multiple sources, apply weights as we said before, calculate the sum, there is a threshold that if we pass the threshold, the neuron firing, so the information is transferred. So the transfer function is very important. Why? Because the transfer function, the activate function, transfers this information, one, and the second, its first derivative is used for learning. I'll explain later. There are many activation functions. The most common are the hyperbolic term, this tangent is practically a symbolic function that ranges from -1 to +1. The sigmoid or logistic activation function is a S-shaped curve, as you can see, that smoothly varies between 0 and 1. It is good for classification problems, for binary classification problems. And the important thing, as I said before, is if we take its gradient, the first derivative, imagine, this is the first derivative of sigmoid function, imagine as that the learning, it depends of how smooth is this. If the learning is a ball that moves along this trajectory, if the derivative is not smooth, this ball may be oscillate between the 2 points and the network will not learn, cannot learn. Imagine the ball can go down easily, not abrupt. So it's important to know if the first derivative is smooth and how smooth. Here is the tangent. See, here it is derivative. How fast it learns because the slope is graded. Okay, it's learning faster. And there are other. This function, ReLU, has faster training. Okay, is rectified at linear unit. This is modern, and the most people use this. Another ReLU. And here we have the architecture, how the neurons connect with each other and connect with output. The simplest is a single layer feeding-forward neural network. Contains only input and output layers. This is the input layer, the information, tail, 4 legs, color, and the output is dog, woman, flower. This is the output. But this architecture does do nothing. Cannot learn.
Yeah, I have a question about how the way we apply the weights. Is it trial and error?
Very good question. Unfortunately, again,
okay, and it's based on our
unfortunately again, as before, as explained, the prediction, the forecasting is more art than science. That means that is trial and error. The starting points, we see this before.
Good morning, Professor Hanias. Good morning to everyone.
Good morning, Professor.
Good morning to my 2 students here. Okay, very nice.
So it's based on our intuition.
Yes, it's trial and error. There are some techniques that we can estimate, but in practice, nothing of this is working. Okay. So, to try to have a better learning and solve nonlinear problems, we put another layer of neurons. This we call it hidden layer. In this hidden layer is this hidden layer works as memory, as a processor that learns. There are many architectures, many types of neural networks. Well, the learning process, initializations, weights receive initial random values. It's very important at marking to begin with a fixed random seed. Because if the program, the software, the commercial software, you must look, if you use a commercial software, that must give you the possibility to fix the random seed. Because if we start with different initial weights, the results will be slightly different, and we don't want it. Initialization, forward propagation. Information moves from input to hidden, from hidden to output layers through activation functions, as we said before. Error estimation. Here is the learning. The difference between actual and predicted outputs determines the network performance. And we choose what margin I will put between target and real target and calculate output. And if the error is not satisfactory, the error is propagated backwards to adjust again the weights, and the procedure starts again. Again, if the error is not the error that I want, going back, then we try and error again, until the target value and the actual value are very close. This is the classic backpropagation network system. As I said before, error calculation, backward propagation, gradient computation. Here is the first derivative as said before, weight updates, and so on. Now we will understand why the stationary plays important role. The activation functions, as we looked before, the output of logistic activation function is between 0 and 1. Okay? And the same, 0 and 1 is the tangent from 0, from +1 to 1. So the artificial neural network works only with values between 0 and 1, or +1 and 1. But our data are not in this area. So we must transform our data in the range between 0 and 1, or +1, -1 and 1. We must transform. This means scaling. The minimum and maximum method, there are many methods for scaling. Look, I want to scale my data between +1 and 1. The scale input is, be careful, mark me here, input, my value, the minimum value of time series, the maximum value of time series, the minimum value of time series. This procedure scale our data. But I want the output of the network to give me the real data. so must unscale. The unscaled output, look this, has the standard deviation. If the time series is not stationary, what time deviation I will choose? The first point, the middle range, the last range. Every range has its own standard deviation. So, the output is wrong, and the prediction is wrong. The same happens if choose another way to scale our data. This way. Scale input. Input, this is the mean value of time series. Standard deviation again. Unscaled output is the scale output. It includes the standard deviation. If our time series is not stationary, I cannot have a good prediction. Another method for scaling. Here is standard deviation. Unscaled output against standard deviation. Plus mean. If the mean is not, if the time series is not stationary about mean, what happens here? Bad prediction. This is why we must make our time series stationary. Another scaling, another procedure for scaling is the Z-score standardization. There are many others, they are not only this. Okay. Now, the optimization algorithm, as I said before, the learning is a supervising procedure, so we must have a way to teach the neural network to learn. There are many ways to teach. All these ways have a common target: to minimize the mean square error or the normalized square error. If the normalized square error is equal to 1, that means that the neural network calculates only the mean value of time series, and its prediction is the next value, which is the mean value of the other values. So this must be near 0. And the mean square error must be minimized. It must be minimized. All the optimization algorithms use techniques to minimize this and this, or one of these. Now, the stopping criteria. When the training is stops. When weight changes become smaller than a threshold. That I say about it. I declare it. Loss improvement. Training stops when improvement in error becomes negligible. Goal achievement, when an error falls below a target value. Early stopping, this is very useful. When validation error begins to increase, preventing overfitting. I'll say about overfitting in next. So I will choose any of these that stop the training, or a combination of these. Now, there are many ways of optimization and learning. Here are the most common. Here is the speed and the memory that each method consumes. The best for time series prediction is to use Levenberg, Marquardt optimization and learning method. It's very speed, but needs a lot of memory. The most common is gradient descent, slow and needs little memory. And here are other methods. There are many, but the most, the best for time series prediction is Lavenberg. I say this because if you use a commercial program about neural network prediction, you have the possibility to choose what method. Newton method, quasi-Newton, Lavenberg quad. Try to use, if you have a lot of memory on your computer, try to use Lavenberg quad. Now, there are the modern neural network architecture is they call it deep learning. What's the difference? The shallow learning has one or two hidden layers with many neurons. The deep learning has many hidden layers, as you see, with less neurons. But this is not a standard way because there are hybrids between these two. And the most important thing for prediction is this. This is when we train a network and have 100 samples, 100 patterns, we call these patterns. I do this. A percent of these patterns I use for training. And find the training error. Measures how well the model fits the training data, the non-training data. Low training error does not guarantee good performance on that data. Mark me in this point. Testing error. I have some data that I will use as unknown data to test the network, and this is the most important part. Measures the model's ability to generalize to unseen data, to unseen. This is for seen data. This is the true measure of performance. Okay. And the goal is to minimize not only this, but this. This will be clear in the next transparency. As an example, we have one hidden layer, and here is the number of neurons. Okay. The blue line is the training error. The what color is? The orange line is the testing error. With the first look, someone will say, oh, if I have many neurons into the layer, 9, look, I have a very small normalized error, p-square error. So I say I will construct a network with a hidden layer with 9 neurons, so it will be useful for prediction. But if we look, the testing error for 9 neurons in the layer is big. So this neural network cannot capture the underlying pattern. If I know very well a poem, I memorize a poem, and I cannot know the meaning of the poem. So, what is the best? The best is to have 4 neurons in the layer, because here we have the minimum of testing error and minimum of training error. But here also is good too. Here I have a good testing error. Okay, but the best is 4. So, if we have too few neurons, too few, 2, 3, I have underfitting. Board model is too simple to capture underlying dynamic, underlying patterns. If I have too many, 9, 10, we have overfitting. Model memorize the diagram, be careful, can memorize the noise and predict the noise. Finding the optimal model is critical. How do we find it? Looking the testing error. How many hidden, what is the optimum hidden layer size? No one's knows it. There are some suggestions. The Kolmogorov said that theoretically suggests 1 or 2 hidden layers that are sufficient for most problems. But it is not always true. Practical rules of thumb. Common approaches using 2 or 3 times the input neurons or the average of inputs and outputs. We'll see in next what it means. So if we have an input of 5, I have 5 inputs, I will construct a neural network with a hidden layer that has 10 or 15 hidden neurons in hidden layers. There are many recipes about it. One hidden layer, look how complex it is. Number of neurons in hidden layers, 3 times the input neurons. Kolmogorov rule, number of neurons in hidden layer is 2 inputs, twice input neurons. This is +1. This is a range. Input neurons divided by 2 to 4 input neurons. If you have 2 hidden layers, look how the number of neurons, how we calculate number of inputs, square root of number of inputs multiplied by n, n is the number of sums, etc. Level 2. Okay. Let's do an example to understand the terms. And the next we use the software. This is the XOR, the exclusive OR problem. Here we have 4 examples. 1, 2, 3, 4. So the n is 4. We have 2 inputs and 1 output. Okay. We have 4 exams, 2 inputs and 1 output. Why say this? Why I will apply this to a time series. The most common use of neural networks is to forecast, to use it for financial forecasting. We can predict stock prices and the most important, the market trends. They say trend is your friend, from historical patterns, weather predictions, energy load forecasting, and every time series that I want to predict, I can use the neural networks. Time series problems, here is our goal. Let's suppose we have a time series that has 100 points. First point, second points, etc. I choose to work with a neural network that has 4 inputs. Why 4 inputs? Because I must start from something. If the embedding dimension is 4, I will try to use 4 inputs. Or if this does not work, I will try to use the time delay. If the time delay is 12, I try to use 12 inputs. Okay? If nothing of this works, I will try to find with trial and error the optimum input, the optimum number of inputs. So, the first example is as input, the first value, x1, x2, 3, 4, and we predict the fifth. What I do, I start from other x2 and predict this. I'll do the same procedure. And here is our last, the today value is our last value. And I say, if the network learn, if he sees 4 values, it predicts the next value. Here are our last value. So can we predict the 15th? Yes. If as learning well its past, we predict its future. Usually we use 80% for training and 20% for testing. This is the training set, this is testing set, and this is the query set. Okay? This is usually. Well, software now in Python. There are many libraries in Python. TensorFlow, Keras, PyTorch, all these are deep learning neural networks, the same now. Okay. Well, we finished this. I have some other things that I will say. As I said before, make a summary. Finding the embedding dimension will determine the number of time-delayed coordinates need to reconstruct system dynamics. KNN prediction, we said before, try to forecast based on similar historical patterns using the embedding dimension and trial and error the number of KNN. Lyapunov exponent will give us, this is the code, will give us an exponent that its inverse will allow us to predict how many steps in the future we predict. What we do? Stationary testing. This is the software. The trending, if there is trend or cycles. This is the software. Hertz exponent, we don't say that. Normalization to scale the data. Network, backpropagation, this is the software. Deep learning, neural networks. This hybrid is between NKNN and deep learning. And we will see now in using the software. We have some parts that we did not explain, but in what time I will explain about Hertz exponent. Normalization of data, but I want to show you examples how we predict using the neural networks. Well, first, I want to show you the stationary test. Let's take the air passengers. Well, this file has 144 points. I have the opportunity to divide the time series in two parts and examine the mean and the standard deviation for the first part and second part. But I can divide in 3 or more parts. I will do for 3 parts and say well, 4 parts. Here is the mean value. Look, for the first part, the mean value is about 100 and something. This is. For the last part, the mean standard, the mean value is about 400. The margin, the gap is huge. This is not stationary about the mean. Let's see the standard deviation. Let's see the standard deviation. Here we have about 60. And here this is 25. Look, the gap. This gap, this gap, this gap. So this time series is not stationary. If I choose another time series, the Lorentz, we will see different. 4 again. Four is very small, it's -8. I will every four points. Now is it correct? Well, maybe it looks big difference, but look at the values. 7.44, 7.88 is stationary. About the standardization, see the mean is full stationary. Okay, this it does not need to make it stationary. Okay, let's go to use the neural network now. Well, again, horizon. How many steps in future will predict? Let's choose 10. Numbers of neurons in a hidden layer. This is a hybrid between deep learning and classical backpropagation. How many neurons? Let's try a hybrid. it has two hidden layers. Let's number for neurons in hidden layer 2. Usually is the half of the first. Epochs. How many times it will be training? How many cycles? 1,000? 1,000. Test size. How many for the percent? 20%? I will choose 20% of our data for testing. So I write 0.2. Validation function. From all our points, I can, during the training process, during, not when it stops, during the training process, I can keep some data, 10%, to validate, to see if the training is good. 10%. This is my original time series. The result, let's see it. Well, until this dot line is the training procedure. Here is the testing procedure, the green, and the red is the out of sample prediction, beyond last value, beyond unknown data. Let's zoom in. I can zoom in. Okay, but the test, the real test is to take these values, the future prediction, as I did before, copy, go into Excel, putting here, paste. Well, the original. These two were by KNL prediction, you remember before. Let's test also with neural network. So I will plot all of this to see the difference here. Insert what? Again. I'll remove the preview. I'll do again the same. Insert. It is too good. Well, I'll remove this. And you cannot see the rest. It's too good. It's too good to be true, as we say. Too good to be true. Look how good. See? Here is the values. You can compare 1.82, 1.88. Here is, I see better here. The difference is in second decimal. So, with this neural network, it works. This does not mean that this architecture will work in other time series. I played with the number of neurons in hidden layer 1 and hidden layer 2 and find this. Okay? Because if I run again, if I run it again, again. The same horizon, but I will change the number of neural networks in the layer. Let's do this and do this. The same epochs. The size the same. Validation fraction the same. No, 1. Time series. Okay. I'll take the values as before. I'll put them in Excel again. I'll make the plot again. And the plot. Oh. Very bad. The green line is the new neural network with different hidden layers, with different number of neurons. It's not good, see the difference, but could capture the trend. The significant point is not these two curves going together, but see the trend. What is the trend? It falls and rise. This is the meaning. And if we try the first neural network again, but in this time I will try to predict many points in future. With the same file, using the coaching data, you will make practice at home, try different architectures, and by experience we will understand which is the best. Again the same. No, wrong. I want many times in future. Again. 10. Please, 15. 100. Again. 20%, 10%. Let's see. Close the. Let's see. how do we stop here? Because it's bad prediction. Well, look at this. Until 12 points, the prediction is good. See, it happens. This is because the system is chaotic, and it's unpredictable in long term, but it's predictable in short term. Okay. Let's try another neural network, a hybrid. Again, the file. Here we put the value dimension, because it is a hybrid. 3. Number of future predictions. 10. Epochs, because it's deep learning, it needs fewer epochs and time consuming. Bad size. What is the bad size? You will face it. Bad size means every 32 points will make a prediction in steps of every 32 points. If your time series has many data, this must be bigger. If your time series has not many data, this must be shorter. No one knows the optimal value of bad size. It's trial and error too. Usually it's common to use 32, but no one knows the exact value. It's more experience. It comes from experience to use the correct value. Doesn't work. Is it something wrong in the back code? I will do this smaller. Okay, the smaller works. 16. This is the model loss. This is the mean square error of training, but we don't. This does not guarantee that the learning is okay. Here is the out of some prediction. And here is the values. And the training mean square error, very small. And here we have the predicted values. Let's test with this network, with the actual points, and see if it was good too. see, I used the basic dimension. Let's see the first, please. Was not well. The blue line is the original. This was the previous network, and the new one is this. Changing the number of neurons in hidden layer, changing the back side, changing also the percent of training and the percent of validation and percent of testing, changing the batch size also. See how many parameters there are. Maybe we get better results. Well, do you have a time or we have a...
Yeah, we still do have some.
Pass the time. Pass the time.
No, we did not pass the time. We still have.
This?
Yeah, we still have like a. We have like 30 minutes left.
You have 30 minutes? Okay, good. Well, do you have any questions about neural networks? Yes.
Yes, my name is Hanias. I come from the University of Passau. So, did you choose the AI algorithm through trial and error, or there was some strategy?
There are genetic algorithms that you can use it to find the optimum values of hidden layers, maps. They do the same thing. They run every time the network changing, as an example, the number of hidden layers, of neurons in hidden layers, giving a range to search from 5 to 100. The algorithm tries to find which value of neurons, number of neurons, minimize the mean square error, and it suggests that use this architecture. But as we said before, there is not a guarantee that minimize the mean square error will take good results. All these algorithms, the AI, doing the same thing, try to find the minimum mean square error. But as we said before, this does not guarantee that the network learns. Usually it is overfitting. We end in overfitting. For this reason, there is not a black box that has a universal use. Every time series needs its own treatment. You must try to capture the dynamic. If I use, I'll check it, the same architecture with check data, with passengers, I will write this that was good, but it left passengers. The same. The same. The original time series is the Australian air passengers. See how bad it is. The original data is the blue line, but this architecture does not work. Understandably, the trend is okay. The trend up, down, okay. But the absolute values are far away each other. If I play with number of neurons, maybe I will succeed. Okay. I will return in neural networks, but before I will have time to give you another tool that will help us to investigate the trend, especially the trend. And this tool is the Hertz exponent. This will help us well, measuring long memory. The Hertz was a hydrogeologist that tried to measure the. He made analysis looking the reservoir of water in Nile Dam. Practically, from time series you can calculate an exponent. This exponent called Hertz exponent. It takes three values. Then if it is near 0.5, this means that our time series is a random walk. It's random, it's unpredictable. Okay. If the component is between 1 and 0.5, this means that the time series is persistence that has long memory. What long memory means? Long memory means that large values are followed by large values of the same sign, and small values are followed by small values of the same sign. If this value is between 0 and 0.5, we have the anti-persistence. The values change the next period, so small values are followed by large values and vice versa. So we have an estimation of what will happen in the future. In this case, the Hertz value is near 0.5. And this is unpredictable. We don't know what will happen next. So if we take a time series of stock price and see in this time period the Hertz value, the Hertz exponent is near 0.5, don't make predictions. You don't know what will happen next. This is the other case that the Hertz component is near 1. This means that, look, small values followed by small values, and large values followed by large values. So in this period, from here to here, we are rather sure that the price is going down. Here, is near 0, we have an oscillation. Up and down, up and down. Large values, small values, followed by large, large, small. Okay. Let's do it with software, as before. And see the air passenger again, the example of air passengers. The air passengers. Do you remember what the first passenger was? Time series. Let's see again. Well, we don't need Hertz exponent of the start to see what this means. There is a trend, okay, and the Hertz exponent gives about 1. This is there is long memory. If I try it to Lorentz time series, the first exponent is about .8, so it's the same to have long memory. Okay. The other thing that we try to show you is how we will make stationary a time series. Let's go take again their passengers. Look, this of course is not stationary. You can see there is trend, we examined it before. Making the transformations, we take this. The first difference, this is the first differences. One way. The other way is the log transform, take the logarithm. And the other is the z-score, where is to divide the standard deviation. You can see that in this case, the time series is stationary. You don't need to make the analysis, but if we take this part and find the mean and standard deviation, and take this part and find the mean and standard deviation, it will be the same. Here is not the same. In this part, the mean we saw before is small, at the end is big. So with this transform, this is the stationary time series, and you can use this for prediction. Also, the same is using the z-score method. Okay, the log doesn't work good. If this failed, you can take the logarithm of first differences, or take again the second derivative. But if apply transformations, there is danger to lose the information. Especially when we try to find, and I'll show you the bend dimension, the fractal dimension. There is a famous article of Tenkens who says, don't glitch your data. Don't glitch your data. Because if we transform our data, there is a danger to lose the dynamic. Okay? Let's try to see how to compute the bend dimension. The bend dimension, there are many methods. One method is, as you said before, with false negatives. I'll show this. I cannot mark the well, I will take the Lorentz time series. I know before the delay time. And here is the method of false neighbors. What say that the percent of false neighbors that is under the threshold, yeah, gives me the ring dimension. The ring dimension is 3. And the Lorentz system has 3 variables. Okay? So, using this is the threshold, we know exactly the ring dimension. And here is the result. Okay, you can use it. Well, I want 3 moments to make a break.
Sorry, we have like 10 minutes left. If anyone wants to ask another question,
yes, but
they have to ask.
A danger. The battery is low, low for this reason.
Okay.
You must put the battery. Of course, I don't know if one try to download the codes or use it during the session. Or any questions? I have more software to show you with neural networks in R and in Python, but the procedure is the same, choosing the parallels and making the prediction. Yes?
I have a question regarding the scaling you were mentioning.
What?
The scaling.
Yeah.
Yeah, for example, I don't know what would be like more appropriate. For example, if you have like a linear system and you just scale the data, I get the the scaling will affect also the, it will be affecting the
Yes,
dynamics. So
exactly. If the system is non-linear, a good question. The transformation may corrupt the linearity. Why Taken said don't reach your data? This is the reason. Don't reach. But if you don't reach, our data, we will have the danger of having different standard deviations, and when I scale or unscale the neural networks, you have bad results. If all of these were easy, anyone would be coupled to the. As I said before, each time series has its own code. We try to find something, starting points. For this reason, we use the bend dimension, we use the delay time. Okay. Which delay time? The delay time that comes from mutual information, or the delay time that comes from autocorrelation function? And which value? The first minimum, the half max value, or the 1 divided by E value? There are many rules of thumbs. As an example, some say that in phase speech reconstruction, you can use number of neighbors 3, 4, or 5 times the intelligence of I said before. Sometimes it works. Most times does not work, unfortunately. So you must try to find the optimal parameters. I'll run another neural.
So our camera's battery is about to run out, and we have to finish it because we're gonna
Okay, so we finish.
And also we're gonna take science.
Sertifikasını imzalayacağız liste gibi.
Yeah, we're gonna also take science for the certificates.
Okay.
Okay, so we have to keep it up. So we have to finish now.
Okay. Please try to download.
I tried, I scanned last
No. Does not work.
Yes, I scanned.
Well, I will. Autocorrelation. Autocorrelation function to find the minimum delay time. Again, the same file. I tried how many lags I will use to find the optimum. You can put any number here. I'll try with 100. And this is the answer. Well, here is the first minimum. I can use this value, and the program gives the exact number. I can use the A divided by E value, okay, and as a starting point, It's a problem with the mouse, as you understand. Right. Again. Well, the first local minimum is at lag 12. I used before 4. Or you can choose this value 7. Okay? Using the calculation function. I can also use the mutual information. Which will give me the nonlinear here exactly the same procedure again. This is more robust. Here is the first minimum, and the lag is 9. The lag is 4. The lag 4 that I used before. Lag 4. Okay. So using the autocorrelation and mutual information, mutual is more robust. We take the lag time, the minimum. And we use the program that I showed before, predicting with K and N. So this is the we finish using the phase space reconstruction and how we can predict using the method of K and N. And we continue with the presentation. Well,
Farklı değiştirdiniz mi? Tamam. Bu genelde dursun o zaman. Ama biraz düz koy. Bak yamuk ekranı yan görünür.
Data preparation. Before doing all this and the next steps, we must examine and see these key aspects. Is the time series stationary? Is there any trend? Is there any seasonality that we must remove the trend and seasonality to have a good prediction? And the goal is to prepare the data, clean data, to meet assumptions for all forecasting, effective forecasting. What is the stationarity? Let's see some dogs, and we measure their height and find the mean value. The green line is the mean value, and see how diverse some dogs from the mean value. We can calculate the variance and calculate the standard deviation, classical statistical things. Well, let's see something different. There is something different in this time series. This time series, in all time, has the same mean, the same average. The next time series has not the same average, the same mean. So, this time series, we say, is stationary in mean. The other is not. If we take two parts of the red time series and calculate the mean from the first part and calculate the mean on the second part, the means would be different. The second picture gives two time series. They both have the same mean, the same average, but have different standard deviation. And the third has the same mean, the same standard deviation, but different variance. Okay. Stationary requires constant mean and constant standard deviation over time. Non-stationary shows trends. So, to have a robust prediction, we must examine, and if it is not, we can make a time series to be stationary. Mean, stationary, non-stationary, the red one, stationary, the green, non-stationary about mean, non-stationary about standard deviation, non-stationary. Here are two examples. The second one is non-stationary in mean, stationary variance, stationary mean, non-stationary variance. Here are some data types. Of course, here is not stationary. You can see them. The same here. Okay. Here there is a seasonality. There are peaks periodically. The same here. Okay. And these are the seasonal are monthly sales of beer production, stock index prices, daily change in index, etc. Fortunately, we can clean our data, removing the trend and removing the seasonality. As an example, here we have original data. We can see that the trend, there is a log trend. We can see if there is not seasonality. And here, if we remove from this time series the trend and the seasonality, we have these data which are what? These data are stationary. So, it is difficult to predict this time series. Look here, this mean and this mean. But it is easiest to predict this time series. If we calculate this mean and this mean, we find the same. But it is not also the mean, it is the standard deviation. And the standard deviation will play a very great role in neural networks. So, we can face this problem easy, very easy. How? Again, using the program dtrend. Well, dtrend. I'll take another data. The classical air passengers, Australian air passengers, is a classical air. Here we are. The original data, there is no stationary, you can see.